Here's the whole proof. Our assumptions are that all the lambdas are distinct, and this linear combination is the zero function. So this is equal to 0 for every z. And we are proving that all the coefficients a1 through an must be 0. So because this is a constant function, all of its derivatives are 0, so we take the first derivative, the second derivative, and all the way to the n minus first derivative. And we set them all equal to 0. And this must be the case for every z. So because that original function is a constant function, all of its derivative would be 0 functions. Now, we can choose the simplest z, which is the 0, plug in 0 here, and that simplifies this linear system. So we get this system of equations. And then this can be written in a matrix form this way. It's a homogeneous system of equations. Now, to the contrary, if we assume that not all a's are 0, then we can come up with a contradiction at the end. And that is enough to prove that all the a's must be 0. Because if we assume they're not, then we have a contradiction. So if all the a's are not 0, then this homogeneous system has a non-trivial solution. Therefore, the determinant of its coefficient matrix should be 0. If the determinant of this matrix is 0, then the determinant of its transpose is 0. And the transpose is the one that's related to the polynomials. So this is the transpose. And we form a new homogeneous matrix equation. So because the determinant is 0, then this equation must have some non-zero solutions, perhaps more. In fact, there are infinitely many solutions. So we assume that b1 through bn are not all zeros. So we have one non-trivial solution at least. Now we write this matrix equation in n equations with n unknowns, the b's being the unknowns in this case, and we are assuming such unknowns exist without all of them being 0. Now notice that you have the same lambda and raising it to different powers from 0 all the way to n minus 1. So this is a polynomial evaluated at lambda 2, similarly at lambda 1 and lambda n and so on. So this polynomial b1 plus b2z plus b3z squared so on to bn z to the n minus 1 has lambda 1 through lambda n as zeros because you have zeros here. What's wrong with that? This is a polynomial of lower degree than n, and it has n distinct zeros. Remember, one of our main assumptions at the beginning was that lambda j's are distinct. So what's wrong with that? We know that a polynomial of degree n has exactly n zeros, so there's no way for this polynomial of lower than n degree to have n roots or n zeros, and that's the contradiction. So therefore our assumption that not all aj's are 0 is wrong. Therefore all aj's are 0. So that proves our theorem.